Hey guys, so this is chapter two, or at least a portion of chapter two. I think this is lecture number 5 for my physics course. Energy, law of thermodynamics. So let's get into it. So, what the heck is energy? That's a really good question. And we have an archaic and outdated definition coming up on the next slide, I think. And then we have types of energy. Uh, since we first defined what energy was, then we figured out there were other types of energy. And so our first consideration of energy, as far as not ours, but humans as a civilization and the advance of knowledge and the birth of physics, Isaac Newton, the whole thing, energy was defined relative to mechanics and mechanical energy. So machines, cranes, steam locomotives, things of that nature, they would take an object and they would push it or pull it like a steam locomotive hauling freight, and it would travel a certain distance. So there was a mass that was a force was applied to it across a certain distance, and that was the first way to calculate energy. Okay, and that's where the original definition of energy comes from. And then as we started studying energy more, we started studying the behavior of heat transfer, and we figured out heat was a form of energy, and it behaves according to certain rules. And we find that for a lot of these rules, it's not just thermodynamics is literally heat and motion, pertaining to heat and motion, but really the laws of thermodynamics can be applied to all types of energy. Um, so determining methods of energy transfer, and that's what energy does. After we consider the laws of thermodynamics, the first one we're going to encounter is the conservation of energy. And that's for classical mechanics, Newtonian systems, things of that nature. And we're going to see that some of those ideas actually pertain to X-ray science, and then other times it's more appropriate to develop a quantum understanding of some of the principles of X-ray science. And so we kind of cherry pick ideas that fit well into X-ray science for explanations and lean on those. And part of that is the conservation of energy. We lean very heavily on the conservation of energy. It explains where the Bremsstrahlung photon comes from. It explains where the characteristic X-ray photon comes from, and so on and so forth. And so methods of energy transfer, I like to call those phenomenon. That's my definition of what phenomenon means, is you witness an event where there's energy transfer, either just one form of energy just converts into another form of energy, either naturally or by man-made machines, engineered machines, made to exploit the rules of physics for practical use. And that's just what engineering is. Okay. And so those methods of energy transfer, those phenomenon, that's what's going to be foundational to X-ray science. How do we make the X-rays? How do the X-rays interact with matter? Those are all energy transfers or energy exchanges, and so they're all phenomenon. Photoelectric effect, Compton scatter, Bremsstrahlung, characteristic emission, all of these things can be described as a type of energy transfer. Not always the same energy transfer, but we start with one form of energy and we end up with another form of energy. So, and there's always loss to heat. That's also one of the rules of thermodynamics. So, and then we are going to briefly touch on, because they make a point in every radiologic science textbook to mention E equals mc squared. And some of them even mistakenly call this the relativity equation. It's not the relativity equation. It's energy mass equivalence equation. or the dual conservation of energy and mass, which is a better understanding of the conservation of energy. Relativity is the idea that different perspectives yield different truths or different observations. That is, just by standing in a different position than I am, and we both watched the same event, you're going to have a different recollection of how the event occurred than I will, because your perspective is different. Okay? And then special relativity, which eventually yielded the energy mass equivalence formula, E equals mc squared. Special relativity is the idea of, okay, what if the observer is moving at the speed of light? How does their perception change relative to a static observer or someone moving at very slow speeds relative to the speed of light? And so that's Einstein's theory of special relativity, and out of Einstein's theory of special relativity was the conclusion that there is an energy mass equivalence given by E equals mc squared. So, all right, so the definition of energy that every radiologic science textbook says, it's the ability to do work. So that implies a potential to do work. But if you study college physics, they also say that it's equivalent to work. So either the ability to do work as a potential, or actually doing work, and there's a very specific definition of work, is energy. You need to use energy to do mechanical work. And that's pretty straightforward. I mean, that makes sense. Yeah, like picking up a sandbag and walking it across the floor. You have to exert a force on the sandbag, okay, in order to change its velocity from rest, so zero velocity, to some velocity, your walking speed, right, across a distance, okay? It takes energy for you to do that, okay? And so that is the first definition of energy. The ability to do work reflects that we started understanding energy by understanding mechanical energy first, and coming out of Newton's laws of motion. This was the easiest way to say, yes, energy was used up. The proof is a mass was accelerated across the distance. Okay, you multiply all three of those together, and that's the amount of work that was done. That's the amount of energy that was consumed. Okay, so that's the first definition of energy, but it does have holes in it. Okay, so you also do energy when you don't move the object. Okay, you use energy, you burn calories, definitely, you get exhausted. Let's say you have a 3-ton weight and you're trying to, now it's not a friction-free surface, it's a big giant block of metal on a tile floor. So there is some friction, but more so, it's just massive. And you, by your lonesome, with no equipment, no pickup truck, no tractor, just you and your arms and your legs, you push for all you're worth, and you can't get that thing to move. Okay? A physicist would say, well, there's no energy because you haven't moved anything. You haven't accelerated an object across the distance. Okay? Even though you've grunted and strained and sweat and worn yourself completely out, and so therefore you have burnt calories, a physicist would say, by this definition, would say you haven't done any work and you haven't used any energy, therefore. And so it's not a great definition. Okay, it's not, because we do understand that energy in calories is related to energy in joules. Okay, somehow, some way. And if you take college physics 2, I'm sure they'll explain to you how to convert calories to joules. Calories is, yes, you guessed it, the imperial system, the English system. Um, but I think they've switched to BTUs, British thermal units. So um, energy is measured in joules on the human size scale or bigger. So, and then of course kilojoules if we're talking about astronomy. And like the output of the sun is probably gigajoules. Um, so with human-sized quantities of energy, joules is an appropriate scale. Joules is a good unit of measure. But in X-ray science, we're going to be talking about the atomic scale. We're going to be talking about individual photon energies, binding energies of the atoms, um, and the energy required to push an electron around. And that's actually the definition of this smaller unit of energy, electron volts. And so I've got the same stuff on the next slide. Let me just go. Yeah, you see, I repeated myself here. And so an electron volt is the amount of energy you need to push an electron through 1 volt of potential. So you have a 1 volt battery pushing against the electron, driving it a certain way around the wire. If you're pushing the electron against its push exhibited by the voltage, the energy you would need to move it to that higher energy state through 1 volt is about 1.6 times 10 to the minus 19th joules. It's a very small quantity of energy, okay? But electron volts are very useful as far as that tiny quantity of energy because that is the scale of the energies of light photons, X-ray photons, thousands of electron volts for X-ray photons. Binding energies, 69.5 keV is the binding energy for the K-shell of tungsten. And so electron volts are the quantities of energies we're going to be using more often. So that's why I showed you the conversions. So joules is the SI unit of energy, but it's far too big when we're talking about electrons and photons. So mechanical energy coming out of Newton's laws of motion, our understanding of gravity, friction, machines, and even your skeletal muscles. They have potential and they have kinetic. There's 2 types of mechanical energy. So potential energy is usually like a counterweight on a crane. Okay, it's to balance the crane so that the crane cable can lift a heavy weight on the other side of the crane. So you might notice the crane is built like a T structure, and it's got a big cement block behind the operator's cabin. That's the counterweight, so that when you pick up a heavy object with the one arm, the useful armature of the crane, it doesn't immediately fall over because it's imbalanced. Okay? And so you can say that the counterweight has a potential energy. Okay? And our gravitational understanding of potential energy, that's where this formula comes from, and the third bullet point there. mgh is the product of the mass of the object. The gravitational acceleration constant, which we learned before, is 9.8 meters per second squared. We learned that in Newton's laws of motion. And then the height of the object from the surface of the Earth. Could be the blacktop or the parking lot, the cement, could be natural ground, whatever it is, whatever we agree upon is the surface of the Earth, the point where falling stops. Okay. And so this potential energy, think of potential as a potential to become a visible energy. And in the event of gravitational potential energy, it's the potential to move or to specifically to fall. Okay, so any object that is suspended at a height above the surface, if it comes loose from its supports, like that counterweight, yes, it will start accelerating toward the Earth. And as it does so, it picks up velocity, okay? A downward direction velocity, because it is a scalar. Okay. And what we're seeing is the object is trading its potential energy for kinetic energy. Okay? Now, there was energy involved in getting that big counterweight and the entire crane up in the air in the first place. And so that energy didn't go away. It's technically being stored by the counterweight, and the entire upper part of the crane is effectively holding on to potential energy. If the crane becomes unbalanced, that potential energy will become kinetic energy, and the crane will start to develop a velocity toward the ground. Okay. Kinetic energy, whether it's gravitational or any other force. Okay, so we're not specific about the force. It doesn't have to be gravity. Kinetic energy is just the energy of motion. If you have an object that's moving, it has kinetic energy because it has a mass and it has a velocity. And so the two terms on the right, m and v squared, velocity squared, are satisfied. And so that's going to be some positive number. Okay, because the velocity will be positive because it's the original direction of motion, and the mass will be positive too. Okay? And so kinetic energy is always positive. So also potential energy is always positive. In fact, energy is not allowed to go to negative numbers. Okay, it's a special quantity where a negative energy, it really doesn't make sense. Okay, if you do a calculation, and in fact this is how the positron was discovered, if you're doing calculations in physics and you end up solving for negative energy, you probably made a mistake. Okay, you might have a negative duration of time, check that, or you might have a oppositely charged, in the case of the positron, you might have an unknown electron that's wandering around with an opposite charge instead of the correct charge. And so there's a hidden negation in there that you weren't aware of, and that negation manifests as a negative energy. It's not really a negative energy, it's positive energy, but you've missed a minus sign somewhere. Okay, other types of energy: chemical, nuclear, electricity, magnetism. Those are the same things. We'll learn about that later. Heat and electromagnetic radiation. And so, yeah, nurses, get the heck back from my acronym. You're welcome to use electronic health record, EHR. But if you say EMR around me, I'm going to assume you're talking about the photon stuff. Okay? So, sorry, we had it first. James Clerk Maxwell. We didn't invent the electronic health record until sometime in the 80s and 90s. James Clerk Maxwell beat you by almost 200 years. So, find another acronym. All right, chemical energy. The energy released from chemical reactions, breaking or creating bonds. And so a chemist would say, oh yeah, exothermic type reactions. Exothermic means that it gives off more heat. The nature of the chemical reaction gives off more heat or energy than it takes to start up. Hydrocarbon combustion in the presence of oxygen is a good example of an exothermic reaction. Okay, and so if you have gasoline or wood or anything else that contains hydrocarbon chains, and then you add spark or flame or even laser and oxygen, then you can start breaking hydrocarbon bonds, and it's exothermic. And so the energy of the first hydrocarbon bonds breaking creates the opportunity for, it releases enough energy that's enough to break more and more hydrocarbon bonds. And so you get a chain reaction. Okay. And so that's how combustion works, basically. It only takes one spark and the right fuel, hydrocarbon to oxygen ratio. It's about 20% to 80% air, 20% fuel, and a spark, and bang, you have fire. Okay, you have combustion. Okay. Another example of chemical energy is the battery. Two different metals in an acid bath is an easy way to make a battery. And they will exchange electrons through chemical reaction via the acid. And in doing so, they will create an imbalance of charges, which if we hook up the two different types of metal to a conductive wire circuit, we can actually conduct electricity and push electrons around that circuit because of the chemical reaction that's happening inside the battery. Okay. Nuclear energy, radioactive decay. We figured out, I think it was Mr. Fermi figured out, that we can actually accelerate this process, okay, by confining it and creating more collisions with some of the decay products and other nuclei. Okay. And so you can get a neutron emitter in particular, and it will collide with other atoms that haven't decayed yet, and it will trigger a decay. Okay. And so it becomes an exponential acceleration of the rate of decay. That's called approaching critical mass. It's basically the same thing happening inside a nuclear weapon. In a nuclear power plant, we calibrate with cooling rods, right, and a cooling tank of water to try to accelerate radioactive decay, but keep it under critical mass, just enough so that it boils the water in the tank, creates steam, which pushes a turbine. Yes, every nuclear power plant is actually a steam power plant. It's steam under pressure pushes fan blades, which turns a magnet in a coil of wire, which creates electricity. Okay. And so that's nuclear energy. Really, this is probably the only mention we're going to have. Maybe in radiation protection radiology, you'll come back to this. But again, we're only just dipping our toe in. We're not getting in very deep. They are cousins to us. They do deal with radiation, but that's what I've described here to you is about as far as we get. Okay. Electrical energy and magnetism. Sorry. I needed a drink. Electricity occurs within the conduction band of the atom. More on that later. Okay. So the conduction band, it's not really a shell. It's the absence of a shell. It's basically once the electron reaches a certain energy threshold, it's no longer tethered to an individual atom. Like in the sake of copper, the valence electrons in copper, it has such a low conduction threshold that basically copper has random wandering valence electrons. They don't really tether to a specific atom. They wander from atom to atom within the copper. Okay, and usually that's random, but if you apply a voltage across the copper, you can steer them to move in one specific direction through the wire, or shift back and forth if it's alternating current. So more on that later. So electricity is the resulting energy from moving electrons through a conductor in this conduction band. Okay. A good example of that is the light bulb. We get light from a light bulb that is an incandescent, but also an LED, from passing electricity through it. Okay. In the original version of the light bulb, it's thermodynamic emission, which we also use in the X-ray tube. The new LEDs, it's semiconductor, it's gaps in the conductivity band. And the gap between two different types of semiconductors is about 2 electron volts, or 2.5 electron volts for green, or 3 electron volts for blue. And then once you have red, green, and blue, you can create any color in between by different combinations and intensities of those three diodes. Okay, we can make LEDs all the way up into the ultraviolet spectrum, but there is an upper threshold where the conduction gap between the two materials gets too big. All right, and then magnetism, more on this later too, is basically electricity, or it's caused by electricity, and it's effectively the same thing. Okay, it just manifests differently, and we detect it differently. But magnetism is the result of charges moving around. Okay, and so if you have electricity, you have magnetism. If you configure magnetism in the right way, you can generate electricity. Next type of energy, heat energy, thermal energy. Temperature measures the heat contained by an object, but it doesn't really measure heat transfer or heat consumption. Those are different calculations. So temperature is really average random kinetic energy of the molecules of the material, or the atoms if you're dealing with elemental copper or something of that nature. So atoms are always wiggling and jiggling around, okay, except for at absolute zero. We'll get to that. And so they always have a certain amount of random motion. The more motion the component atoms and molecules of a particular material have, the hotter that this thing is, the higher its core temperature. Okay. And so heat transfer is actually the transfer of these vibrations, these jigglings of these atoms. And so as conduction and convection work on classical physics, it literally is atoms colliding with atoms, and then the motion, part of the motion, is transferred to the new atom. And so that's how heat spreads out, is through conduction, direct contact, or convention, where the random motions are transferred to fluids, either liquids or gases, and then the fluid starts circulating because atoms with more kinetic energy tend to rise inside the volume of either the gas or the liquid, and colder, less mobile atoms tend to fall. Okay? And so examples of heat energy, the toaster and the X-ray tube itself, those convert, both of them convert X-ray, or not X-ray, electrical energy into heat. The X-ray tube also makes X-rays. So you're saying it's a glorified toaster? Parts of it resemble a toaster. The filament definitely resembles the toaster coil, the things that you see getting red hot. That's also thermodynamic emission. So if you look down into the toaster and you see there's wires on the side of, like, where the bread goes, the hole where the bread goes in, and you look down in there and you can see the wires getting red hot, that's thermodynamic emission. Okay. And so that's the same thing we rely on at the cathode filament and the X-ray tube to produce excited electrons. Okay. All right, electromagnetic energy, just really quickly, it is fluctuations of the electric field and the magnetic field. The only difference between those two, remember, that's the same thing. The magnetic field is always oriented 90 degrees to the plane of the electric field, though. And they've tried to draw it here, but I don't know, the perspective is just off. It just looks weird. I I like my drawing better, and so in the electromagnetic radiation chapter or lesson that I'm going to give, I think it's chapter 4, don't quote me on that. Um, I've got a different diagram of an electromagnetic wave, and it looks a little bit better. It's the same principle as what you see. The z-axis is the direction of the photon travel. The electric field is oscillating along, I would call that the y-axis, and the magnetic field is oscillating along the x-axis. Okay, um, and they've labeled those E and B because that's what physicists use to describe. Capital E is energy, but it's also the electric field. Capital B, not small b, is the magnetic field. Okay? I guess was capital M taken? I don't know. Maybe there's confusion there. So uh, it is a wave-like energy disturbance that travels through space at about 3 times 10 to the 8th. Well, yeah, about 3 times 10 to the 8th meters per second. Okay. Other types of potentials. So we covered mechanical potential energy, but batteries, voltage in particular, is said to be electrical potential energy because it is the motivating force to push electrons. So if you have a voltage, all you need is a source of electrons. And batteries, effectively, the chemical reaction that will take place if you connect a wire is a potential to conduct electricity. So batteries are said to contain electric potential energy. It's really chemical energy, but it's electric potential energy, okay? Because it has the potential to become electrical energy. Gasoline and other hydrocarbons contain chemical potential energy because the ease of the combustion. They have the ability to combust readily, and there's just some things that are classified as flammable, right? And that's why we have the big warning stickers that are safety yellow and bright red. Because we know that hydrocarbon combustion in the presence of oxygen is an exothermic reaction. It'll run away from you. And so it's dangerous. And so gasoline and other fuels, other flammable things, have chemical potential energy because they have the potential to burn. And when they burn, they'll release heat and light. Okay? Isotopes that have not decayed have nuclear potential energy, and that's where our diagram, this illustration stolen from the internet, I'm so proud, of Schrodinger's cat. Okay, so you won't find that diagram in the textbook. They tend to avoid Schrodinger's cat because it's a little screwy, and he's trying to make a joke about how quantum mechanics doesn't make sense. But um, the thing is he proposed this as a farce, and everyone said, "Yeah, that totally would happen," and he just kind of face palmed and walked away and didn't want to talk about it again. So if you haven't heard of Schrodinger's cat, it's worth a story, and it does describe nuclear potential energy. So in quantum mechanics, an individual radioisotope atom, that is, it has the potential to decay. Now, unless we observe it, we don't know if it's decayed or not. So one of the ways we could observe it is we could get it to turn on a electric crane uh, or shut off an electric crane like the yellow device such that it no longer suspends um, its load, which is a hammer. Okay? And so the crane only turns off and drops the hammer if a decay occurs. But this is inside a closed box. So we have no idea. Well, you might think, well, we might hear the sound of the hammer colliding with whatever that is. Okay? Well, Schrodinger said, well, this thought experiment, you can't open the box. Okay? And you can't hear or see inside the box. Okay? And so It's a box and you have no idea what's going on inside. But you do know that there's an isotope in there that is the trigger mechanism for a crane that's holding up a hammer over a glass vial that's filled with poison. And there's a cat in the box. If the glass vial breaks, the cat will lick up the poison and die. Okay? And so this is the chain of events that has to happen. Radioactive decay causes the crane to turn off, causes the hammer to fall, causes the vial to break. The cat licks the poison that was contained within the vial, and the cat dies. So after deductive reasoning of about 4 steps there, if a decay has occurred, the cat's dead. If a decay has not occurred, the cat's alive. Okay? But quantum mechanics says until we measure it, we don't know if a radioactive isotope, a particular atom of the radioisotope, is decayed or not. We don't know if radioactive decay has occurred until we measure it. And so basically what Schrodinger was saying is until you look inside the box, because the isotope is in a superposition of decayed and not decayed at the same time, until you look, the cat is also in a superposition of both alive and dead until you look. Okay? And so it's a farce. Cats don't occupy a superposition of being both alive and dead at the same time. The cat is either definitely alive or definitely dead. And opening the box does not make the cat descend into one of the two energy states. That's ridiculous. Okay. But this is also plausible. If you follow the logical conclusion of quantum mechanics regarding radioisotopes, then this is totally plausible. And until you open the box, you don't know for sure if the cat's alive or dead. And so you have to assume that the cat's in a superposition of being both alive and dead until you open the box and make the determination. So you could say the cat is potentially dead, I guess, if we're talking, as long as we're talking about potentials. Okay. And then high energy EMR is in a potential state because it has the potential to create an ionization. And that's an energy transfer. And so usually it's, what is there a good potential for? Oh, falling. Oh, electric shock. Oh, burning. Okay. And so usually it's, there's a specific phenomenon that this thing is likely going to undergo given the right conditions. Right? For high energy X-ray, it's ionization. Okay. For the battery, it's conduct electricity. For gasoline, it's burn, combustion. Those are all predictable phenomenon. And so the potential energy that they possess is the high probability that those phenomena will occur given the right circumstances. And that takes us to our laws of thermodynamics. It's really a bad segue going from types of energy. So this was originally meant for heat, and there originally was only 3 of them. Okay, and the first one's supposed to be the conservation of energy, but I tacked on this other bullet point regarding energy flow. So abundance to absence. So where energy is to where it isn't is basically how it flows. Okay, via conduction, convection, and radiation. Okay, until equilibrium is achieved. That is, in the case of heat, if you have a hot object and a cold object like a heater, and then a human being, and the human being is cold, they turn on the heater produces heat, and then that heat spreads through the room via radiation and convection. You could touch the heater directly, but you might burn yourself. You will transfer heat to your tissues probably more rapidly than you want it to. And so Convection and radiation it spreads out in all directions, and so it's less efficient than conduction. But eventually, heat spreads from the radiator and starts warming you up in the cold room. And so the heat is being transferred from abundance. The radiator or the heater has plenty of heat, but the human being has an absence of heat. And so over time, the human being absorbs the heat and the radiator gives off the heat. Okay. Now, if this is not a closed system, if the radiator is plugged in, it's taking in electricity from outside the room. Okay. And so the conservation of energy doesn't really apply in that state. But if you had heated up a chunk of iron on a fireplace and then stuff that chunk of iron under your mattress, you could actually use that to keep your bed warm all night. That used to be how they would do it, is they would heat up a piece of iron, not so it was red hot, but so it was warm, and then you'd stuff it under your mattress, and it wouldn't be warm enough that it would catch anything on fire, but it would be warm enough that the iron bar would transfer its heat to your mattress, and then your mattress would feel warm for a significant amount of time until your body heat warmed up the mattress and you were already asleep at that point. So, conservation of energy. This applies to closed systems, but it has been modified since Einstein discovered that energy and mass can be exchanged in certain scenarios. So the conservation of energy for classical mechanics and most of the stuff we're going to encounter and describe, energy can't be created or destroyed. Okay? Now, in a closed system, that means the energy you start with is the energy you end up with. Okay? And so when we look at the photoelectric effect, we're going to look at the conservation of energy before and after of all the players involved. Okay. When we look at the Compton event, we'll look at the conservation of energy formula to account for all the energy we start out with and then all the energies we end up with. Okay. And those are phenomenons, so there is a transformation of energy. Okay. Now, entropy is the teenage boy's bedroom rule. A system tends toward disorder. Okay. And that's kind of like, think of the first bullet point, the hot object and the cold object. Okay. After a while, the hot object is going to send away its heat and reach an equilibrium with the surrounding air. And that means the molecules within the object will be moving about as much as the molecules of the air in the room. Okay. And so heat flow will stop at that point because there is no abundant object that has more heat energy than any other object in the room. So there'll still be transfer of heat, but it will be balanced. Okay. In other words, and the heat will be relatively uniformly distributed through the entire system. Okay. You can always add in more energy from the outside. In some circumstances we do. And then you can see that equilibrium is not achieved. But that's because you're artificially adding energy to the system from an external source. Okay. If you include that external source in your system, you expand your system to include that external source, then you should find that the conservation of energy holds. Okay. Now, entropy, teenage boys' bedrooms. A system tends towards disorder. Okay, so it takes energy, all moms know, to fold your laundry and put it away. And all teenagers know that dirty laundry goes in the no, not the hamper. It goes in a pile on the floor. What are you? No, you just put it in a pile on the floor, and then in a couple days it disappears. And then you come home from school one day, and all your formerly dirty clothes are now resting on the edge of your bed, and they're folded, and they're just waiting for you to take care of them. And if you're a teenage boy, that may or may not be a priority for you. You might just leave them there if they're at the foot of your bed and they're not hurting anything. Why do they got to go in the drawers? Why not just leave them on the bed until you're going to wear them the next time? So I'll stop there because I'm triggering some folks. So, all right. Um, so what's happening is the categorization of the distribution of items takes energy, okay? But it doesn't take energy to not care for organization, okay? And so just randomly placing things down wherever it's convenient, and now there's no organization and the system is disordered, okay? All right, so that's how messes are made. But let me explain to you how entropy also describes heat distribution through a system. So you have a hot object and a cold object. Well, that's a categorization of the items in the system. You're able to sort them into an order. You have a bucket or a category over here, hot objects, and you definitely have an object that's hotter than the other ones, and so it belongs in that category. And then you have other objects that are not hot, they're cold, and they belong in that category. But as heat transfers from the hot object to the cold object, now they start, after a certain amount of time, everything comes to the same temperature in the system. In other words, there is no way to sort the system between hot objects and cold objects anymore. And so entropy has increased. That is, I have lost a way to sort the system. Okay? Kind of like if the pile of neatly folded clothes were in the teenage boy's way and he just shoved them onto the floor where there were dirty clothes. And so now you have a pile of clean clothes formerly folded that are now mixed with the dirty clothes. And so there's no way to sort that. Yeah, well, there's still your sense of smell. That might help. Okay, I'm triggering people again. I need to stop. All right. So then the final rule, which I'm really not going to explore much, is as temperature approaches absolute zero, kinetic energy in the system approaches zero. Now that's going to be an important concept in MRI when we talk about superconducting magnets or superconductive electromagnets to create larger magnetic fields by reducing resistance. But other than that, we really don't consider scenarios where we're really close to absolute zero. It just doesn't come up in conventional X-ray. All right. So the book totally calls this, as far as I know, Bouchon calls it the relativity formula. It's not the relativity formula. Okay. And so they don't, Adler does, or Carlton and Adler don't do that. They just say that the equation was described in his theory of relativity. It was actually described in his theory of special relativity. It was a necessary consequence of special relativity. Okay. If you're interested in that derivation, I'm sure you can find it on YouTube. I'm not familiar how he got to that from an observer traveling at the speed of light, but it's in there somewhere. Okay. And so matter and energy have a unique relationship. Matter really is energy, and energy is matter. And we can actually convert matter to energy in special case scenarios. And so Einstein said E equals mc squared if you have some kind of nuclear decay or an accelerated nuclear decay, like a nuclear weapon or a nuclear power plant, then by losing a little bit of mass through the decay process, you can produce a large quantity of energy from a small amount of mass, because c squared is like 9 times 10 to the 16th power, I think. Yeah. And so you multiply a tiny quantity of mass times 9 times 10 to the 16th, which is c squared, and you get a large amount of energy. And this is kilograms to joules. So you don't even need a full kilogram, and you get a really, really huge amount of joules. So, yeah, so as you run these specific reactions where it's accelerated nuclear decay, energy will increase while mass decrease. And so you do consume the fuel rods over time. They have less and less isotope in them the more that you use them, and eventually they don't have enough isotope to produce a yield, and the fuel rods have to be changed out. Okay, so what does it all mean? Well, there's some key ideas that you have to consider. Anytime we're changing energy, some energy is always lost as heat. Okay, so there is going to be energy given to the molecules and the atoms, and maybe even the electrons, such that they produce motions of those things. And that's heat on the atomic level. Okay. Technology is about exploiting energy conversions for predicted outcomes. So as we figure out, as we do the imagination part in the physics classroom, the engineers say, hey, I can build a machine that will plow a field because of this, or I can light up a room because of this, or I can create electricity because I can build a machine that creates electricity because of this. And so all technology, all invention, all industrialization comes down to we figured out how to make energy, or how to change one form of energy into another form of energy, and that new form of energy has some kind of use for us, either lighting up a room or warming us up or moving something or whatever. Okay. Since we're not considering nuclear fission or fusion, right, in X-ray science, we must start and finish with the same amount of energy. So they went to great trouble to teach you E equals mc squared, just for me to tell you this is the first and last time we're actually going to use E equals mc squared. Well, not true. Nuclear medicine will use E equals mc squared. Okay. But really, yeah, plain X-ray, we don't use E equals mc squared. So they mention it because everyone recognizes it, literally. Okay. And half of them give it the wrong name. It's the energy mass equivalence formula. Okay. Since we are not performing the exam, the X-ray exam, at absolute zero, entropy will increase. That is, disorder and randomization cannot be eliminated. And so we get disorder and randomization when we try to create an image. Some of the energy does not behave and do what we want it to do. Some of it just goes off in a random direction. We call that Compton scatter. We can reduce the appearance of randomization, but we can't completely eliminate it. And then finally, so that means we do have to apply the conservation of energy in that fourth bullet point. And then finally, understanding can be achieved by taking an inventory of the object and the energy, what objects hold on to the energy, what objects are lacking energy, and then at the end of the event, has the energy transferred from one object to another? Has the energy changed its form from one type to another? And so really that's how we describe these events happening, is describing the objects involved, and then describing the energy transfer between those objects. And that's basically the event. That's all we understand about the event. Okay. And so if you can categorize those things and take an inventory of the objects and the energy that they possess at the beginning, and then describe how that changes through the event, then you understand the event, because that's all anyone understands about, like, photoelectric effect and Compton scatter. Right. Conservation of energy and entropy and heat exchange and energy conversion. There's always some loss of heat. Well, the X-ray tube is extremely inefficient. It only produces a 1% useful output. 99% of the electrical energy is wasted as heat production inside the X-ray tube. Okay, and so if you want to make a billion gazillion dollars, you will figure out how to make a more efficient X-ray tube such that we can get up to even 3 or 5% X-ray production. Hadn't been done yet, but if you can make that X-ray tube, you can create significant cost savings in electricity usage. And you will necessarily produce less heat too, so it'll be a more durable X-ray tube. The heat produced in an X-ray tube is a concern because the vacuum actually impedes two of the mechanisms. Okay, conduction is limited. The glass envelope becomes really, really close to the rotor stem, and so there's kind of a conduction happening there at the rotor in the glass envelope. Convention is right out. There is no air. There's no fluid inside the X-ray tube. It's a vacuum. And so the anode can't lose heat by convection. It either gives its heat to the rotor or it creates infrared energy that it just broadcasts along with the X-ray. And so both of those are how the anode loses heat. And then the rotor is actually, by conduction and radiation, is able to give heat to the glass envelope, and then the glass envelope is bathed in oil, and so that's convection because the oil's a liquid. Yeah, the entire tube housing is filled with a insulating oil to pull the heat away from the glass envelope. Okay. The anode, the rotor bearings, and the filament can all suffer heat damage. And so that's why we're really concerned with thermodynamics and heat energy, because the X-ray tube does build up heat quite efficiently. And occasionally, if we run too large techniques too fast, we will have to cool the X-ray tube down before it's safe to use again. Okay, so that is your tour of energy and thermodynamics. This is pretty sure that was lecture number 4. Wrapping it up, going home. I'll upload this to YouTube in the next couple of days. I'll see you guys later.